Now, being in a metropolitan city, Istanbul seeks solutions for today and future generations, like worldwide New York, Tokyo, Mexico City. So I'd like to invite Giacomelli for Horticulture for Future and Space.
I normally don't start off by telling a joke, but if I did, I would start off by saying an archaeologist, an art historian, and an engineer walk into a bar. For those who understand, I'll stop right there, and I'll move on with my presentation. It's an honor and a privilege to be here, and I want to thank Yüksel Tuzal and Murat Kachira for the opportunity to be here, without which I'm sure I would not. And then I want to think about all of you. You don't know me. I know some of you. But I know you came to this event. And I came to my first one 9 times ago, in 1982 in Hamburg, Germany. And I was privileged to meet people, engineers and scientists, that would put activities together to develop food systems, horticultural systems, to feed people. We didn't have much at all of that opportunity to study together in the United States, and I'm glad to see that those opportunities existed. Today, there is GreenSys. Every 2 years, scientists and engineers working on controlled environment agriculture get together. And next year in Angers, France, in June, they will meet again. And they still have a lot of work to do, because there are challenges out there. I don't know if you know the Rolling Stones. Some people say they're the greatest rock and roll band in the world. We certainly can say they may be one of the oldest rock and roll bands in the world. But I like the words that I see here about a storm is threatening our lives today, and I need to get some shelter or I'm going to fade away. And one kind of shelter that will focus on controlled environment, greenhouses. This is a picture of one of our greenhouses in Arizona on a very stormy day right before I left last week. And the opportunities that we've taken over the years to develop control systems, from high tunnels to vertical farms to plant factories to space events as well, and rooftop greenhouses. And they all essentially exist using controlled environments and hydroponics. The benefits, a lot of zeros, and that's a plus in this case. 0 emissions, 0 nutrient runoff, 0 pesticides if you have a good IPM program, 0 herbicides, especially for growing in hydroponics, and therefore no soil-borne diseases. Hydroponics, essentially growing without soil, requiring some hardware, a pump, to pump nutrient solution through a network of pipes, to irrigate the root zone of the plant, to collect any excess runoff from the plants, bring it back to storage, and have controls and sensors to make sure you maintain a good nutrient solution. Dr. Murat Kachir, my colleague, has put together this system, growing just in sand. The sand does nothing but support the root system. All the nutrients in the water comes from the fertigation system applied by drip irrigation. And then the extreme, the semi-closed glass greenhouse, a standard complex glass greenhouse, in this case with very little venting. An engineer in the group would say there's very little vents if you're going to be cooling this greenhouse. But it's a closed system, and it's engineered to work even with very little or no ventilation. Which leads us to urban agriculture. The modern production, the desire for the young people today and others to bring food production into the metropolitan areas. And I'll be showing you some examples that we list here. First one on the Whole Foods market in New York City. This is a high quality food, vegetable selling facility, is a greenhouse, Gotham Greens. And we're proud to say that one of our students formed a company that created this and now has 6 greenhouses throughout the U.S. Another one of our students, Elaine Patterson, in the middle of this picture, is working at Green Sense Farms in Indiana, which is an indoor vertical farm that is a multi-layered growing system, allowing no sunlight in, using all electrical lights for growing the crops. Benefits of less water. You look at 5 to 8 times and many more if you look at vertical systems per unit of crop, and certainly less land space. That means these systems are flexible enough to go into locations where you might not be able to farm at all, or not even having the soil that could produce a crop. I bring this up for my breeding colleagues. Environment with genetic potential gives us the value of our crops. Without both, we would be into big trouble. And controlled environments now can really bring out the genetic potential for crops in the controlled environment even better than in the open field. My topics of discussion, which may become a little bit abbreviated here as we move through, talking about systems and their implementations, talking about applied and fundamental research by giving you examples, and then talking about education and how we have to outreach to give people opportunities, and then some final thoughts. But first, an advertisement from our sponsor, the Controlled Environment Agriculture Center at the University. Our mission is to develop controlled environment agriculture that is economically, environmentally, and socially sustainable agricultural option. Not to replace field production agriculture, but to complement it in the best way possible. From these doors, this building, these people, students, faculty, staff, work together to focus on energy, water, nutrients, capital, and labor. Let's look at some of these systems. Example, vertical farm, Dr. Mariah Kachir and myself, we're working on indoor growing and demonstrating that to educate the students, have hands-on experience. Some of the crops, lettuce and basil that have been grown. And yes, even Marat gets in the pictures. Sadler Machine Company and the South Pole Food Growth Chamber is another application. This essentially was a project with the National Science Foundation to provide a food growth room, an environmental room, so that people could sit and watch the plants grow when they live in an extreme cold and dark environment at the South Pole throughout their 6-month-long dark winter. This has been in production since 2004, and when 60+ people overwinter at the South Pole, they have fresh vegetables for a salad every day of that time period. Another image from inside is showing the multiple layers for the small crops as well as the tall crops that are located in the center of the room. All controlled environments, all using hydroponics. Phil Sadler, Sadler Machine Company, goes further and says we should leave the planet, go to Mars, go to the moon, and put together a habitat that you see here. This is what he envisions. What I envision is part of those cylinders at the end of those fingers being a lunar greenhouse, is what I was going to say. But also that it has to be buried. And that's one to show you that we can put this together and protect from the galactic cosmic rays, because there's no atmosphere on the moon and very little on Mars. And we work together internationally. People in Italy and the US, students, faculty, staff, about the prototype lunar greenhouse. Here it is, 5.5 meters long. It's a cylinder that's lightweight and it's collapsible. It mounts better in a rocket this way, that there's no corners and sharp edges. Definitely NASA-like structure. Here we are a couple of days after the transplants have acclimatized, and here we are about 30 days later in a highly productive closed-loop system for hydroponics, recycling the nutrients, as well as recycling the atmosphere, with the concept being that the oxygen is produced from the carbon dioxide that the humans put out to provide the oxygen for the astronauts to survive. And the water is recycled as well from the plant transpiration. It's condensed and cleaned up, and it can be used for drinking water. And then, of course, we have food, the biomass, actually, for production. And one last thing that never gets in the slides and is forgotten many times is the psychological benefit of people wanting to have green plants in an extreme environment and enjoying that taste and the fragrances and of being more like at home. Some of the crops that we've demonstrated in the system are cucumber, tomato, sweet potato, potato itself, basil, and strawberry, as well as lettuce. That's very common. Applied in a different way on Earth is aquaponics, growing the fish, using the waste from the fish that produces the ammonia to convert that into nitrate and to feed it to the plants. In the process, then the plants give back clean water that can be recycled for the fish, and you do not have to discharge any water. Let's look at some applied and fundamental research examples. Dr. Kachira again, and Dr. Giacomelli will be discussed here significantly. Murat speaks much about sustainability in controlled environments, and not only producing food, but also producing energy simultaneously through the glazing to improve the sustainability of the system. Here's his example, now in his sand bed greenhouse, growing tomato and operating completely on the photovoltaic cells that you see in the background for cooling and for pumping of the nutrient solution. Changing the glazing that could provide the photovoltaics directly inside itself, sharing the photons of light to produce electricity and also photosynthesis. He did studies to demonstrate the viability or lack thereof of production using the reduced light that the plants get, and the trade-off therein, if you have no other power source available, it's a very acceptable solution. He also likes to monitor the plants remotely and non-contact so that we can feed back information to the computer systems that then give us not only data about how the plant is growing, but can actually change the environment to improve how it's growing. Challenges on Earth remain with cooling. It's much more difficult to cool than it is to heat a greenhouse, particularly in Tucson, Arizona, but other places as well. And this international project, with the support from BARD, put together information and strategies for controlling the environment using fog evaporative cooling and reducing the amount of fan capacity that you need in fan ventilated greenhouse or without any fans in a natural ventilated greenhouse. We also do substrate studies to try to improve the microbiology aspect of the root zone, and we're working here with Premier Tech to improve production of tomatoes, particularly during our stress periods of the summer in the desert Southwest. Cherry Kubota has left the University of Arizona and now resides at Ohio State University, and we wish her the best and we wish to begin collaborating, but I have to show you her work for the past 16 years, much of it as a plant physiologist and a horticultural engineer. to develop sustainable production technologies and some new technologies. I'll show you some pictures to give you an idea about strawberry production, increasing yields by 300% compared to the field, producing the crop during the winter period, not competing with the California produce, and having it available during our holiday seasons, and using 20% less discharge. And here, Mark Krogel, working with cherry, demonstrating melon production, providing 75,000 melons per hectare on a yearly basis. That's a lot of biomass. Of course, it's a lot of water too, but it's also good quality water. Beautiful. Transplant production and use of grafted transplants to reduce the need of transplanting in the open field. A lot of people here have done this work as well, particularly because of the lack of fumigants that will be available to use in the field. Using LEDs as a means to affect the crop morphology, its growth characteristics, and even its productivity of phytochemicals in the plant is work that Cherry has done with Ricardo Hernandez, a graduate student who's now a faculty member at North Carolina State University. Increasing market competition. Cherry tomato, it's sold because of its sugar content. So we measure Brix, total soluble solids, and we can increase the Brix content by the electrical conductivity, the intensity of the fertilizer in the nutrient solution, and increase it significantly, as you see in the graphic here. As well as a phytochemical. This was lycopene was a study, and we could show a 20 to 40% increase in lycopene for a given tomato under high EC conditions, and followed up with a nutritional feeding study with our nutritional science department, because putting the lycopene increase in the fruit is not as the same as having that available for people to utilize during consumption. However, traveling in space under the harsh conditions of the radiation and the stress conditions of the extreme environment, this kind of work will continue to be very, very important for other aspects other than lycopene itself. Next to the end is education, instruction, and outreach, and we claim that we put short courses together on a regular basis to bring growers and want-to-be growers to a level of understanding, at least to know what questions they need to learn more about in a short 5-day period, and then we follow up with consulting as well as additional classwork. You see a picture here of a classroom. It's a 500 square meter classroom that we use. Every one of our students coming through our controlled environment program gets hands-on experience with producing at least a tomato crop, if not more. Here's an example of Miles Lewis teaching the floating graft lettuce production system, again, to growers or growers that want to get into this business. And this is a rooftop greenhouse. Our student center manager, Todd Millay, decided that he wanted to provide fresh vegetables for the student pantry at the student center, and put his money where his mouth was and built this, and we should be transplanting this coming week our first set of cucumber, tomato, and sweet pepper to go into the student pantry at the student center, which is food that is given away free to students in need. A big exhibit at the University of Arizona Biosphere 2. It's the 1.5 hectare facility, all glass, fully enclosed, now 25 years old, with well-established ecosystems that we were able to put a bioregenerative life support system, or our Mars greenhouse, on display. You can see Phil's habitat and the bottom right, and then people watching the plants in the yellow lighted lunar greenhouse around the corner. Some of the crops that we produced in there shown here. Final thoughts. Successful food systems will be achieved if we have a fundamental understanding and we implement controlled environment agriculture and hydroponics with good environmental control in a protective facility using a flexible design, monitoring, evaluating, automating, and we need experienced growers and producers. And we will, I won't, but someone will do it on Mars someday. My expectation is that we learn how to grow grape in the greenhouse so that my great-great-granddaughter can have a glass of wine as she lives on Mars. Take home. Controlled environment technology exists today. It is functional, it is commercially viable. In the 1990s, we didn't know what we were talking about. We do now. Capabilities are that we can produce plants for our needs independent of climate, predictably, consistently, and with a quality that people will desire on a regular basis. The challenges: education, education, and more education of young people, of people who invest in these systems, and of the dreamers who are dreaming new systems. We cannot break the laws of physics, nor can we break the laws of biology to make a plant grow. It will just not do anymore until a long time into the future. We need financial support, we need sensors, better sensors, more sensors, direct control from the plant, and we need creative applications. People like Phil Sadler that dream up these things and said, yeah, we'll put a system together and we'll test it. Ultimately heading to urban sources. Therefore, with knowledge, technology, resources, the capability to market within a food chain, and with good business investment, wise business investment, we should help to feed the world with controlled environment agriculture. So, why are we here today? Because of food for life, for our life, and for all future life. I would, if I could, raise a glass of wine to you right now. We will shortly. I think you're all ready. I know I am ready. And toast the fact that it is a good life, it can be a good life, and we need to make it such. And back here, it says, bridging the world through horticulture. I would amend that and say, bridging the worlds through horticulture. All of you know how to do it. We need your help. Let's go. Thank you very much for your time.